So there is something about remote sensing that can kind of turn you into a superhero. Well, at least it can give you some superpowers. You can see things that you would otherwise not be able to see. And it's all because of this strange thing called spectral signatures. No, it's not time to call Ghostbusters. It's time for a little bit of physics. Let's have a look. So, of course, you're very familiar with the visible wavelengths of light. Those are the things that our eyes can see, and that they sit in this much, much broader EM electromagnetic spectrum of light. In fact, the visible wavelengths of light are only a very, very small part of the EM spectrum of light. But what Sentinel-2 and other satellites can do is to see into those wavelengths of light that we can't see, and allows us to access them. So if you take a look at a typical landscape that you'll find in Northern Ireland, this is Glenariff Glen in the Glens of Antrim. And you can see here the different surfaces and all of the different colors. Now, what is it about those surfaces that gives us or allows us to see those different colors? The answer is the different wavelengths of light that those different surfaces absorb and reflect. And the different ones that they reflect towards us allows us then to perceive them in different colors. So from that, we go into a rather bizarre question of why is broccoli green, or why is vegetation in general green? And it's to do with this spectral signature that it has. Here is the spectral signature for broccoli and for vegetation. And you can see here in the visible wavelengths of light that it reflects more in the green wavelengths of light and absorbs more in blue and in red. So if it's reflecting green, we see broccoli as green. Now, it turns out, though, whenever you go into these other wavelengths of light beyond the visible light, the spectral signature does something very interesting. Whenever you get into the near infrared, the amount of reflectance of the surface of broccoli goes up considerably. It reflects an awful lot more in these wavelengths of light than it does here. If we could see these with the human eye, broccoli would appear much, much brighter than it actually is. So the reason, just a little bit of quick biology for this, the reason for that is because of the reflection here in the near infrared by the spongy mesophyll, and then you've got a couple of dips here because it's absorbed by water. We'll throw in a little bit of biology for you. So what that means then, whenever we look at the satellite images, that if you only look at the visible wavelengths of light, there is this amount of reflectance in the green. But whenever you move into the near infrared, in other words, when you move into where the spongy mesophyll reflects the near infrared wavelengths of light at a much, much, much greater intensity, then you're picking up an awful lot more light energy and it's appearing much, much brighter. So it allows you to see and distinguish things so much better and so much clearer because you're accessing wavelengths of light that you wouldn't normally access. So, quick analogy here. Different people have different signatures. There's the Queen's signature, there's Harry Styles' signature. I know these days it's not about the signature, it's about the selfie, but occasionally some people, even today, want to get the old-fashioned signature. And whenever people put their signatures down, different people have different signatures. Well, it turns out then that different surfaces have different spectral signatures because of the properties that they have. They reflect different wavelengths of light in different ways. So let's take a quick look at an example of this. This is Kilimanjaro, tallest mountain in Africa, in Tanzania. Kilimanjaro has some ice at the top, or at least it kind of has ice at the top. It's being affected by climate change, but that's another story. There is some ice at the top here, and there is some cloud. But at the visible wavelengths of light, it's not always easy to distinguish between the two. You can probably tell the edge up here looks more like snow and ice. This looks more like cloud, but the bit in between here is a little bit harder to distinguish between. Now, the reason for that is because if you look at the visible wavelengths of light, both snow and ice have pretty much the same, or sorry, snow and cloud have pretty much the same spectral signatures. You can't really tell the difference between them. But whenever you move then into the near infrared and especially into the shortwave infrared, you start to see a difference. And anytime you've got this difference between the spectral signatures, it makes it much easier to distinguish between them. More or less the same here, very hard to distinguish. They spread out here. So this should make them easier to distinguish between. Well, let's see if that's true. Here's the true color image. Here's the shortwave infrared. And all of a sudden, the snow and the ice become much, much easier to distinguish from the cloud. So that's the kind of superpower that you get from this, and it's all because different surfaces, different properties have different spectral signatures, and it's when you get these differences in the spectral signatures appearing that it really allows you to tell the difference between these and satellite images. And as you go through each of your particular projects that you're going to be doing, you're going to be making really good use of geography's superpower, courtesy of remote sensing via the spectral signatures.